And I work in the working group of studying about process work. So today we are going to talk about how in Mainz we compute these nuclear polarizabilities in ionic atoms. And I would like to start with a very influence on my talks. So and the nucleus bound together by means of the electromagnetic interaction. And we really want to study these systems since they have the very nice property that since the muon is much heavier than an electron, the Bohr of ordinary atoms. And this means that the energy spectrum of the bound muon is very sensitive to the details of the nucleus. So this is the reason why muonic atoms are nowadays considered an excellent precision probe for the nucleus, and they have been extensively used over the last few years to study nuclear properties. So one of these studies is the currently ongoing experimental campaign at PSI of the collaboration, which aims on other things. It plans to measure nuclear charge radius across the nuclear chart by making spectroscopy experiments in ionic atoms. And there is already some results that I don't need to go through because there are like some nice talks actually. Several of them. One of these, maybe for historical reason, the most important of them is the Lamb shift. And the Lamb shift is very important because it's an observable that is different than zero only one. The most important of them are these quantum electrodynamic radiative effects. These are the leading order correction, or the contribution to these radiative effects. And the important things to notice is that the nucleus for this effect is still seen as a point-like external source of radiation. One can improve the description of the nucleus, and one can, for instance, improve recoil corrections. So we can give the nucleus some dynamics to move around the space, and this generates these nuclear recoil effects that are small but sizable for ionic atoms. But if we want the most precise description of the nucleus, we need to include also these effects. So we need to include the fact that the nucleus is not point-like. It has a charge distribution, but even more, we need to include the fact that the nucleus has its own internal dynamics. So in case so you can go over like you can do like an electromagnetic transition while it interacts with the left side by counting this equation insertion that they contain. So for instance, this the Prema collaboration in ionic 4. So these numbers are relevant for the ionic 4 ion. And you can immediately see that this nuclear structure are much smaller, but using this number, I mean the Lamb shift in ionic 4 was able to extract this value for the charge radius of the alpha particle and precise the denomination of the alpha or the charge radius of the alpha particle. But you can immediately see that the uncertainty is dominated by theory, which in turn is dominated by this delta NS5 and delta NS6, which for the rest of the talk we will. So it is very important that we keep reevaluating these nuclear structure effects in view of the latest advance of nuclear theory. And this is what I do, how we make these computations in my working group. This is the non-relativistic Hamiltonian for an hydrogen-like atom. And we iterate this analytically But then, like using this corrections in perturbation theories, and the correction we are looking at are the correction that are modeled by this perturbation here. Also, the nucleus that has structure, it has dynamics, and the interaction is between, in reality, between the muon and the nucleons that makes the nucleus. At the very end, this one at the top will be your total Hamiltonian, where this HN is the nuclear Hamiltonian, which is included or not, depending on whether we want to look for nuclear size or polarizability corrections. These are sometimes known as elastic and inelastic contributions. So, okay, at the very end, we can split the total nuclear structure effects into a sum of finite size and polarizability corrections. And we can evaluate here in this talk, we are interested in the nuclear polarizability and evaluate damage interaction of the perturbation and a Green function for the muon nucleus system. And after some algebra and some approximation, keep in mind these points because I will get back to one intermediate step between this expression and this expression later on, maximization of nuclear polarizabilities at order z alpha to the fifth, which is basically given up as a sum of different contribution. And each of these, apart from a coefficient that is known, is given by an integral. This integral runs over an intermediate energy transfer in this two photon exchange process. And inside this integral, we have two functions. This calligraphic f function is known by looking at the electronic particle. What is more a problem is this nuclear response function cannot be obtained from the Feynman diagram. It needs to be evaluated from nuclear physics. And there are different ways to evaluate these response functions, but they will be used in my initial nuclear theory. So when we say that we want to use Ab-initio methods to evaluate this response function, what we mean is that we first want to solve the Schrödinger equation for the nucleus using the least amount of approximation. And then from the solutions we used. An important point to keep in mind is that for this recipe, all of this recipe, the nuclear Hamiltonian is an input which is not uniquely defined. So it is a big source of uncertainty. And in order to move on, I need to explain how in the modern view of doing nuclear physics, we define this nuclear Hamiltonian. So in the modern view of doing nuclear physics, nuclear Hamiltonians are derived from effective field theories. In particular, the effective field theory that I'm using in my work is the so-called chiral effective field theory. It is a low energy theory of QCD that retains all its symmetries, but and this will assess a well-defined hierarchy among them. So for instance, the power quantity scheme you see here is the so-called Weinberg power quantity. Contribution to the observable is expected to be larger than all the others. Then we have some next leading order, next leading order operator, and so on. But this separational scale is extremely important because at some point we will truncate at some order this expansion. But we can, by exploring the separational scale, we can also associate it by other techniques, for instance, Bayesian statistics, some well-defined uncertainty quantification coming from the truncation of the Hamiltonian. And okay, I will show you some results, some practical example in how we do that, take it from my work. And let me start by showing you my what you're seeing here on the left part of this slide, they are all the possible terms that contributes to this effect up to z alpha to the 5. And by summing them up, we obtain these two numbers here. That these are the two. These represent the nuclear structure effect up to the alpha to the 5. Why there are two numbers? There are two numbers because these nuclear Hamiltonians come from two different cutoff choices to regulate the short distance part of the interaction. So there is one cutoff of 1.0 Fermi and one of 1.2 Fermis, and we implemented both of them and did the computation with both of them. Going to the right part, we can see the convergence pattern of this observable as we increase the order of the Carrier expansion. So these points with the arrow bands are my results, and the horizontal line are two previous established computation. You can see that after each step, as we go from the leading order to next leading order, next leading order, we converge towards the previous computation and step. Now we can analyze these uncertainties in a different way. We go to analyze the uncertainties, and this is what you are seeing here. Bayesian statistics allows us to provide statistically interpretable uncertainties to this observable. So for instance, if you look at this NLO in results, this is my results, and this has to be seen as a probability distribution of this truth expansion I've highlighted here in the conference in the paid leading order. Please do not pay precise, but it is not, and I can comment that later if you are interested. And in fact, it is pretty off the previous computations. But the uncertainties are the next leading order, next leading order can be trusted, and the next leading order, which is our most precise computation, we found a result that is totally in agreement with the previous computation from these papers. But yeah, it has to be said, uncertainties for the moment is slightly larger. Now, about these dots, this intermediate step, like this is one of the intermediate steps to get to the final results. And I need to show you this because the uncertainties coming from the nuclear model is not, of course, the only source of uncertainties. There are other sources, and one important contribution is this so-called Eta-expansion uncertainty. So as I mentioned, this is an intermediate step to get to the final nuclear polarizability term. And what we are doing this step is expanding in terms of eta. So this eta, I don't need to define eta for the purpose of this, of showing these results. I just need to say that we are expanding in terms of eta, and we are truncating the expansion at this point. And this truncation comes with its own associated uncertainty associated to this expansion. And these are our results, which we can compare to the previous estimate of this uncertainty. And you can immediately spot that there is a problem in the muonic helium 3, because we have found an uncertainty that is 4 times larger than what's previously expected. So this Eta-expansion seems to converge much slower than what was previously expected in muonic helium 3 for reasons that we don't know. And yeah, this is a problem and needs to be addressed somehow. And we're still discussing how we should address this problem. So finally, this is the last slide. So this is the slide. And we move on to a slightly different topic, because so far we have talked about muonic atoms, but in view of the planned experiments in hydrogen-like, in ordinary hydrogen-like helium atoms, what we have done is reassessing the uncertainties coming from the nuclear polarizability terms in this have been done on this nuclear alpha pole using this expression experimental data, and they got this transition in this electronic ion, and they associated an uncertainties of 10%, which comes from the fact that this equation holds an approximate level. Now, working from the